Hello again. Today's topic is eigenvalues, eigenvectors, who cares? So I want to talk about some of the applications of this theory of eigenvalues, eigenvectors, and I'll have a somewhat worked example to show you how that works in practice. So what I'll say is the utility of eigenvectors and eigenvalues comes from the fact that I'll say higher powers become easy. Okay, what do I mean by that? Well, first note that if V is an eigenvector for A with E value, eigenvalue lambda, then what happens when I take, let's say, A cubed times V? So this is a matrix A. I can take the cube of it. It's n by n. So, well, what do I mean by A cubed? I mean A times A times A. That's a matrix times V. Now, in general, that's annoying, right? I mean, A times A times A, that's going to be a kind of computationally expensive, especially if it's a big matrix. It's a lot of steps, right? But what we're going to do is we're going to use the fact that multiplication is associative. So this is just A times AV. But what is A times V? That's lambda V. And as you know, lambda is a number, so lambda can come out of the expression. This leaves just lambda times 8AV. And same trick, kind of rinse and repeat. This is lambda times A times AV. Once again, what's AV? It's just lambda V, and I'm going to bring that lambda out again. So lambda times lambda becomes a lambda squared AV, which is again, same deal one more time. This is going to then be lambda cubed V. So in general, what this is saying, we have A to the n times V, right? So no matter how high that power is, this is just going to be given by the number lambda to the n times V. So this turns, matrix multiplication into just powers of the real number lambda, which, that's easy. I mean, this is immediately, well, might need a computer still or calculator, but it's just a quick calculation, whereas A to the n could be very expensive. And when you have many matrices or, many large matrices, that is pretty significant. But now maybe the question is, who cares about high powers of matrices? I mean, why would I even want to consider those? And well, there's many places that it turns out that those are relevant, and one of them is, i.e. these are important in, well, certain kinds of dynamical systems called Markov chains. So I'll give you, I don't know if I'll properly define that, but oops, okay, so I don't know if you read this. Okay, so again, who cares about high powers of matrices? Well, this is, one of the main tools in the study of Markov chains, which I'll define via an example. So let me do this with an example. So e.g., suppose the movement, so a very simple, maybe somewhat artificial model, suppose the movement between, say, city and suburbs, think San Marcos and think maybe Austin and San Marcos, I don't know, that might be controversial, but let's say an abstract city and an abstract suburb is given by a 2x2 matrix, the following, and I'll explain what I mean. So 0.95, let's say 0.05, 0.03, 0.97. So think of this as kind of the city column. This is the suburb column. And what I mean by these numbers is that, so the first column is saying that 95% of the city dwellers stay in the city after, say, 1 year. So this is a model that's kind of describing the movement after 1 year. So that's what this 95% is. So it's 5% move from city to suburbs. That's what this is here, right? So in this column, I've got 95% of the city dwellers staying in the city, 5% going from city to suburbs. And so this column is my activity of the suburbs. So this is saying that 97% suburbs stay, 3% move suburbs to city. Okay? This is after 1 year. Let me call this matrix A. Now, what I want to know, so hopefully that makes sense, this is a very simple toy model for describing, the movement of dwellers between city and suburb after 1 year. Somehow in this model, more folks are moving to the suburbs. It's kind of, maybe more like 10, 20 years ago, the situation. But anyway, so this is a model for this particular setup. My question is, what is the long-term behavior? Well, notice, first of all, that if I take a vector v, where, now I take a 2x1 vector where in the first coordinate I have the number of city dwellers, so call that S, or C, I guess, for city, and S is the number of suburb dwellers, right, in the second entry. Then what is A times V? Well, let's work it out. 0.95, 0.05, 0.03, 0.97 times CS, right? And what is that? That's going to give me a vector, of course. And what is it? It's 0.95C plus 0.03S. And what's in the second column? It's 0.05C plus 0.97S. So notice what you got here is exactly what's happening after 1 year, because among the city dwellers that were originally there, we have 95% of them staying. And then we pick up the 3% of the suburb dwellers that moved to the city. So this, and same deal for the second entry. So what I'm seeing here is that AV is the new population distribution after 1 year. And, well, what happens when you apply A again to this population? It's going to be the distribution after 2 years. So in general, if I look at A to the n V, this is the distribution after n years. Okay, so kind of cool. I think it's a nice, way to think about, applying this kind of iterative rule in terms of a matrix multiplication. So in terms of the long-term behavior, we want to describe A to the n V, let's say as n goes to, well, a large number, let's call it infinity. Okay, so this is now a reason you might want to care about a high power of a matrix, because in this model, for instance, it's describing, after, let's say, 1,000 years, what does the distribution of the population look like? Of course, my model's probably breaking down by then, but, again, a toy model here. Okay, so how do eigenvalues and eigenvectors come into play here? So let me just tell you, for A equals 0.95, 0.03, 0.05, 0.97, we have eigenvectors. I'll just tell you there's an eigenvector 3, 5 that has, well, let me call this V1. This has eigenvalue. You can check that this has eigenvalue 1. And another eigenvector is going to be 1 minus 1. Let me call this V2. This has eigenvalue lambda 2 equals 1 minus 1. That's right, that should be a number. So this eigenvalue is, 0.92. Okay, so the vector is 1 minus 1. The value is this number. Okay. Now suppose the original distribution of original population is given by well, let me just write this a little bit artificial maybe, but 511. So maybe this is 5,000, 11,000. So again, remember our convention was the first was the city and this is the suburb. So just to keep the numbers kind of manageable, we'll just call it 5. But maybe that's 5, like I said, 5,000, 50,000. But just to keep the number small, let's take it 511. Now note that I can write 511 as a linear combination of the two eigenvectors. So what is it? It's going to be 2, 3, 5. I know I can do this actually because this is going to be a basis. These two vectors form a basis for R2. So any vector in R2 can be written in a unique way actually as a linear combination. But, let me just tell you that this is the way to do it here, where these are the eigenvectors, right? These are the E vectors. So now apply the matrix A to the n to this, remember we want to know what's the long-term behavior, so I'm going to apply this matrix A to the n, and what you get is A to the n times 5, 11 equals A to the n times 2, 3, 5 minus 1 minus 1. Okay? Well, remember, A to the n is just a matrix. It distributes over a sum, and this coefficient 2 can be brought out. So this is A to the n, 2 times A to the n, 3, 5, minus A to the n, 1 minus 1, right? A to the n, again, is just a matrix. But here's the magic. What is A to the n times 3, 5? So if I knew nothing else, I would have to take A times A times A times A n times. But we know that this, since 3, 5 is a eigenvector, this is just going to be the eigenvalue, right, lambda 1 to the n times 3, 5, minus, well, same deal here. 1 minus 1 has eigenvalue lambda 2, so this is lambda 2 to the n times 1 minus 1. And what are those eigenvalues? Well, we set up here. So this was 2 times 1 to the n, 3, 5, minus lambda 2 is 0.92 to the n, 1 minus 1. Okay? Whew, okay, so lots going on here, but it's actually not too bad now, well, because 1 to the n is nice, so this is just 610 minus 0.92 to the n times 1 minus 1. Now, what are we interested in? We want to now take n to infinity, and if n goes to infinity, well, 0.92, right, I'm just taking 0.92 times 0.92, that's getting smaller and smaller. I'm taking a fraction of a fraction. So this will actually equal 610 minus, this will go to 0. So this is minus 0. So what I get here is a pretty nice answer. It's telling me that in the long-term behavior as n goes to infinity, the number of years goes to infinity, what I'm getting is, right, remember the first entry was the city, the second was suburbs. So this is the sort of long-term behavior is that, well, I've got 6 or 6,000, whatever you wanted to, units you're using here. I've got 6 in the cities, 10 in the suburbs. And, that's the, well, again, for this toy model, that's the complete answer. That tells me, at least mathematically, what this model is predicting. So, again, I think this is one of my favorite, actually, applications of linear algebra, at least at this level. So hopefully you guys enjoyed it. See you next time.